Hello everyone, welcome to our next video on linear regression. So in our previous video we talked about simple linear regression, which was the scenario when your outcome, right, is linearly dependent on your predictor variables, right? But in practical scenario, you just do not have, say, one independent variable, right, or predictor variables. So we'll be interchangeably using many of these terms, right? Predictor, predicted, right, independent, dependent, right? And some other common terms which are kind of interchangeable. So if you just take that, the housing example that you saw, we made a very, very simplistic assumption that price of your house is only determined by size of the house, right? But that is not the case in real life, right? You are having, for example, location, right? That could determine say number of rooms, that could determine many other factors, right? So the moment you have more than one independent variable that determines your outcome, right, then the modeling technique that helps you take care of this is multiple linear regression. We'll straight away, look at the definition of it. You have to pay some good attention, and kind of try and memorize it. It is a very simple extension of your simple linear regression that you saw in terms of y is equal to mx plus c. And those m's, right, which was the factor that measures the difference or changes in your dependent variable as a result of unit change in your independent variable, right, m. That's typically known as actually betas, right? So in this particular case, say x1, right, is just like what you had in case of your house size, right? And if it was the only thing, so you are having some actually multiplier associated with that. For example, every unit change in your house, size of your house determines, changes your price of the house by, say, certain lakhs or whatever. But now you are having, say, number of rooms, right? So there could be some, multiplier. So just like, the way you are having beta associated with first variable, which is, house size, you can have another, beta associated with your second variable, that is number of rooms, or another beta with your location, and many others, right? And as you have seen, we took an example where we were talking about number of hours, studied and marks scored. And we saw a very interesting example that even if someone doesn't study anything, they could still get some marks, right? Not necessarily they'll get zero. So that's actually, the offset that you have, that is beta 0. And so basically what we are talking about is, if you sum up the beta 0 and then multiplication of, the coefficient with each of those variables, beta 1, x1, beta 2, x2, beta, and xn, assuming there are n number of variables, still you might be having some scenario where, there could be some deviation that you not be able to find out. Typically, the way it happens is, in theory, right? In practice, what you do is you focus on, say, a few known set of, predictors, right? But there are many that you are, never going to discover, right, during your process of data collection, analysis, domain related exploration, right, from experts. So whatever explicit predictors that you have chosen for your analysis, and the multiplier that you have, there is always going to be scenarios, where, certain part of it will never be explained. And that's what that you have an epsilon or error term, right? So do remember this formula, as we know, y is your dependent variable, your xi's are your predictors, beta 0 is, we have another name for it, that is intercept, beta 0 coefficient, and, epsilon is your error terms. We have covered it now. This is important when your outcome variable is linearly dependent on more than one set of independent variables, right? And in this particular case, multiple linear regression helps you, understand and model that relationship. Very simple, right? Extension of your housing price. So your price is going to be, that intercept beta 0, right? Which could be something. And then, say beta 1 into area, beta 2 into number of rooms, beta 3 into age of house, right? Or beta 4 into location, and, blah, 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 right? And then, an epsilon. So idea behind, your coefficient determination, that is, beta 1, beta 2, beta 3, right? This is, so we have a way of, determining it, right, based on your data set, right? And we call it, ordinary least square. We'll see that it is pretty similar to what we have been talking about. When we are talking of simple linear regression, we are talking about best fit, through least square, right? Ordinary least square, there is some relaxation on your set of assumptions. We will also review that, and we use ordinary least square to kind of, estimate the coefficients. And when we are talking about multicollinearity, it's always important, when we are talking about, multiple linear regression, whether you have multicollinearity, and how good, what is your goodness of fit, right? Those two are very, very important, key points. We'll actually deep dive on these in upcoming, video in the same lecture. Right? So just to review, what we need to find out here, what we need to keep in mind here is the general, form of multiple linear regression, because this might be asked in your exam, and have this example in mind, right? About your, housing price, or you can actually develop another example of yours, just to keep, main formula in mind. We'll actually sort of, just like what you saw in case of simple linear regression, right? In case of multiple linear regression, when you want to find out the best fit line, right? As you know, since there are multiple predictors, right? So rather than a line, we are talking about an hyperplane, right? And but the overall idea is same, right? That relationship between dependent variable and independent variable, in a way where your sum of squared is residuals, right? Which the difference between observed and predicted values is minimized, right? How you can do it? You'll start with some estimates of your betas, right? Beta 0 to beta n, right? And then we typically use, ordinary least square method, to iterate over it and find out the best fit. This step involves we find out the sum of squared errors, right? Or we also call it residual sum of square errors, by looking at, the actual versus predicted based on your initial guess on betas. You square it up, and then, if you are looking for, how to find out, right? For your coefficient, it is actually in terms of your we will not actually, so the whole idea here is you take transpose, right? on your independent variables, right? And take inverse of that, and then actually multiply with transpose of independent variable and your value to be predicted, right? So this is the general you know normal form that you start with. Typically, finding a closed form solution, right, is always not possible, and that's why we follow a set of methods around ordinary least square to get approximate set of values that minimize this objective that you have in mind, right? Um, yeah, interpretation of coefficient, we have already seen it. Assumptions could be again important, so you can review it, right? uh, so linearity is important, that there is a relationship between predictors and dependent variables linear. What does that mean? It shouldn't be that if your housing prices your actually size of your house goes up by x, your price shouldn't be going by say x square, right, or x cube or log of x or e raised to the power x or any of those things, right? So whenever actually your say price, your size of the house doubles, right, and your price of the house get quadruples, right, those are actually kind of non-linear relationship, right? But as long as it is actually kind of not having any of the squared terms, um, uh, the multiple linear regression can help you capture that. Um, Homoescastis, sorry. So yeah, I mean this is actually very hard to pronounce, but when we are looking at variance of residuals, right, there shouldn't be a trend. That's the whole idea here, right? It shouldn't be kind of increasing or decreasing in some fashion, as long as there is actually kind of random outcome there, which we also call white noise. So basically, the whole idea here is when we are looking at the variance of residuals, it shouldn't kind of increase or decrease in difference to independent variables that you have in mind, right? And that together with residuals to follow a normal distribution, um, it's kind of again another important assumption that you have. Once you've actually kind of modeled it, you have figured out your betas and other things. In earlier case, the simple linear regression, we used mean absolute error or root mean squared error to find out the goodness of fit, right? So the one with the lower value was the better. But when you are having many multiple variables, right? Finding out an MAE or RMSE that can help you interpret independently is very, very too difficult. So there is a term called R squared, and basically, one idea about R squared is this helps you find out, so the way it is actually being said is proportion of variance, right? That is explained by the model, right? And it's basically number varying between 0 and 1. Higher the numeric, better the fit. Another thing, as you see, when we are having some kind of data set, right, when you start using more and more variables, right, you are always, likely to have higher R squared. So, but that might overfit easily. So to avoid that, when you actually increase number of variable, you kind of penalize your R square in some way. That actually kind of discourage overfitting, right? So we'll actually just have the idea behind registered R square is when you use more and more variables, right? You actually use a penalty factor, right? And then as you saw in this particular case, your overall regression model, goodness of it can also be through an FS statistics for part of it. And p values are mostly to test that betas that you are having are significant or not, right? So for set of betas which are not significant, you simply drop them in your final analysis. Okay, so we have covered R square in some sense, right? It's a number between 0 and 1 that actually explains how fit your, yeah, so perfect is 1, totally off is 0, right? Adjusted R square, we talked about it. Multicollinearity is another important, term here. If you see, when more than, two or more variables, independent variables, right? If they are highly correlated with each other, using uh, using them together could uh, im- could actually kind of alter, right, the decision making steps that you are having, right? So here we are talking about p values to determine the test of significance, right? And what happens is when actually your data set are kind of um, highly correlated, um, you know uh, many a time the decision that you are making about betas is keeping the other constant, you know but you can't simply keep them constant if they are perfectly related. If one increase, the other will increase. If another decrease, the other will decrease, and vice versa. So in that sense, you actually run through certain set of analysis and figure out the set of variables which are highly correlated. You remember we talked about correlations. If two variables are typically, say more than zero point 0.8 correlation, you consider them kind of, having some such certain amount of multicollinearity, and then you figure out a way of using representative set of variables out of that. So there are a bunch of actually unsupervised techniques of doing dimensionality reduction or other things. Given the nature of this course, we'll see if syllabus requires us to cover that. Otherwise, we'll not kind of give you too much of detail around that. So related with R square, there's a term called variance inflation factor, and it's just like uh, something like VIF is defined in terms of R square, so 1 upon 1 minus R square, and you look at a range of VIF. When you are analyzing variables in pairs, if for those pairs, if you are having VIF greater than 4 or in some cases 5, you make a decision about whether they are multi kind of highly correlated or not, right? And then if you are finding set of variables which are highly correlated, you figure out a way of kind of dealing with them before going and blindly using it for your modeling. Okay. What we'll do at this stage is we have been talking about housing pricing data for quite some time. So we'll actually, do a walkthrough, right? Um, in one of our, you are recommended for this course, I think RStudio. I'll be showing you, ID for Python, right? Um, you can actually talk to your teachers and figure out what they are suggesting. If in case for some of your internals or others, if they need code in R, you have to actually kind of try that. But we'll simply look at it in Python, and you can find similar line of code to go through these modeling step and have some outcome. But before we change the screen, let me quickly talk about nonlinear regression. So what we have talked so far, we talked about simple linear regression, which was when you just have one independent variable. We talked about multiple linear regression when you have more than one variable, and relationship is linear. But what if your independent variables and dependent variables are not related in a linear way, right? That's when there are variations around modeling that we call nonlinear regression that are used, right? It is very, very important to keep in mind, right? Is uh, you know uh, uh, non-linear regression can sort of help you model much more complex relationships that a very simple linear relationship that we have seen so far, right? So you can look at any of those examples where changes are kind of exponential or logarithmic, or square or cube, right? So say for example, if you have some relationship, say for example you just have two-way data set, right? Where you have y relationship is y is equal to x square. So you have 1, 3, 1, 1, right? 2, 4, 3, 9, 4, 16. If your data set is like that, you can't use simple linear regression there. You have to use a set of techniques that can help you sort of model that. And there are variations, so if you look at some of the common variations for nonlinear models are polynomial regression, which is more like y is equal to x square, y is equal to x cube, and there could be multiple terms that you can see there. Exponential, logarithmic, as you saw, right? So one of the the second degree polynomial, right? Y is equal to 2x squared, right? So plus x, right? So some part of it is linear, some part of it is a square, right? So you find out the coefficient related to that, and now you can actually sort of use these to model your nonlinear relationship. Sometimes what you can do is you can actually apply some transformation and sort of again convert it into linear relationship, and then from there on you can use more simpler as long as you apply those conversion, right, before you go for reporting. You might be asked that how you can use what are the typical steps of using nonlinear regression, right? So very important, look at do your exploratory data analysis, try and find out what kind of dependency is there if it is not linear. Then you figure out whether it is polynomial, which is more like your curve relationship, or exponential, which is more about talking some kind of growth or decay, right? And then from there on, there are actually many of these polynomial regression and variations around exponential and logarithmic that you can use to fit your curve, right? From there on, again, you use a variation or similar to R square sort of techniques and residual plots to figure out goodness of fit, and then you are having a clear model which can actually help you predict, right? In terms of key metrics, R square, adjusted R square, mean absolute error, and root mean square error, we have actually been talking about it. We will come to conclusion, but before that, let me take you through this, one of the example, right? So yeah. So here in this case, we are using, so in SQL library in Python, right? There is a library called dataset. So basically in the SQL you can use dataset package, right? And there you have variety of datasets available. We are using Fetch California housing. It is very similar to the example that we have taken throughout, right? Where we are trying to predict the price of the house based on multiple factors that you are having. Right. So the first part that you see here are primarily importing the required library, which is NumPy, Pandas, and then variation of sklearn for dataset and dividing our data in train and test, right? So there is another video where we have been talking about train test split, cross validation. You can see more detail in that video, and then we are actually from sklearn linear model, we are actually going to use linear regression here, and for evaluating our goodness of fit or fit of this curve, we'll use both mean absolute error and mean square error as well as RT square. Matplotlib is a very popular library for visualization. So the very first step, data is equal to fetch, right? California housing, right? So you simply call that this particular line, right? And you can also, so let me run everything together, and then we'll actually look at the data set, right? So if you see, your data will be having target variable, right? So this is the prices that you have, and then you can look at what are the different features here, right? So you are having, house, age of the house, how old or new it is, right? Number of rooms, number of beds, population in that area, right? Occupation, and then latitude, longitude is mostly, deciding the geographical location of that. Uh, if you so basically what we have done post here is, we have defined our independent variable, that is price, right, from this target, and then we are simply dropping it and saying our x and y. So x is your independent variables, right? Y is your dependent variable, and from there on, if you want to see, right, so you can call sample, right? Say we take 5 samples, right? So you can see the typical values out here, right? Age of the house, average rooms, and many of these things. And you are simply doing 10 trace split, and we initialize our model from a call to linear regression. Then we are simply calling the fit on X train and Y train, and then we can use the Y to predict, right? And there are actually this library for mean absolute error and root mean square error as well as MAE. So you can actually type them. Your mean square here is 0.53, right? Your root mean square error is 0.74, and your R square is 0.57. So not a very good model. It's actually kind of able to explain somewhere about 58%, right? 0.58. Typically, you need R square higher than 0.7. So from here on, we can actually use some other steps where you can find out multicollinearity, then use direction of variable and all, right? And then we have simply kind of plotted this part, right, where you are looking at your price versus your some of the factors, right? Okay, so you can actually play with actually more examples to make yourself comfortable. That's always going to sort of help you better grasp this, as well as try and use with some of the typical problems that you face, right? Yeah, so just to summarize, we talked about multiple linear regression. We kind of looked at R square, adjusted R square, nonlinear regression, and we'll actually look at some of the how your questions are what kind of question you can expect. So MCQ, 100 words and 200 words kind of, right? So MCQs, for example, nonlinear regression, right, can be performed for which kind of variable, right? You saw it continuous. We explained it in previous video on simple linear regression as well, right? Which of these is true? Equation of nonlinear regression follows the equation of a line, right? No, right? It will actually it can follow the equation of a curve, and you know that, right? What is the difference between multiple linear regression and non-linear regression? So multiple linear regression, relationship between your outcome or predicted variable and your predictor is not linear. Is linear, and in case of non-linear, that relationship is not linear. Typical example is exponential, logarithmic one, polynomial of certain orders. We covered about how to what are the steps for using nonlinear, right? So do exploratory analysis, try and actually establish the relation, do transformation, and from there on you can actually use simpler ways of modeling as well. What could be real world scenario for multiple linear regression? Numerous, right? So many of you guys at some stage will be writing some standardized exam, right? Say those of you who are going to some of the foreign universities, so you might be writing SAT, right? Many of you might be writing exam for your grade level schooling and all that, right? So you can collect data, right, from previous years, get some data about demographies that is available and published, in those respective exams. You can look at your CBSE, data points itself that is published, and find out some sample data set around that, and then try and see that how can you predict the score based on some of the variables that are captured. That could be one. House price, right? There will be actually lot many examples. Just look around and see how you can actually best model it. Advantage of using nonlinear, right? So even if there is a very complex relationship between predictor and predicted, you can actually use it, right? So thanks guys for watching it. In next video, we'll take actually your actual exam questions in past, right? So yeah, just join us, for the next video. Do subscribe if you like it. Thanks.